This is tutorial 3, part 1 of course CVG 3148. This tutorial is going to give a quick reminder on how we deal with non-rectangular section, and we're going to look at another example of a non-rectangular beam. We'll also review how we deal with the problem of skin reinforcement. So first of all, let's remind ourselves how we deal with non-rectangular cross sections. So the way we solve this, you can read this paragraph over here, but very simply, we're going to use this concept of force balance. We have to remember where our equations come from. So when we're doing analysis of rectangular beams, what do? We set our force in the tension steel equal to the force of concrete in compression. Okay, so that's this equation over here. Normally, this area of compressed concrete, it's equal to B times A. That's what we have for rectangular beams. For non-rectangular beams, it's not equal to this. So instead of putting B times A in this equation, I'm going to put area of concrete in compression. So that's what I'm going to solve for. So I know everything else here. I'm going to solve for this area of concrete in compression. Once I've done that, I'm going to determine what's this value A. So I'm going to determine area of concrete in compression. Then I'm going to determine this A, and also I'm going to determine this A bar, this centroid A bar. Because again, what do we usually have to determine moment resistance? We have the force in the steel times this lever arm, which is the distance between the centroid of the steel and the centroid of the concrete. Normally, this is D minus A over 2. But when we have a non-rectangular section, it's not equal to that. It's instead equal to this value Z, which is just D minus A bar. So how do you do this? You need to use geometry. So each problem is going to be different, and you're going to have to figure this out. So you have to consider geometry. The other thing you're going to have to do is you're going to have to assume where this A falls. Okay, because the equation you have for A concrete in compression, which you're going to use to determine A, is going to be different depending on the assumption of where A falls. So this is something to consider. You have to make an assumption and then you have to check it. Okay, so there's examples here. So to show that we can use this concept to solve any type of beam, let's look at this strange beam which we are given in this problem. It's a triangular section. You're not gonna find this in practice, but it's just to show that we can determine the moment resistance of any cross-section shape. So you have a triangular section, F prime C is 40 MPa, Fy is 400 MPa, and you have 325 M bars, which are given as in the problem. And you're also given the effective depth of your beam. So we're going to assume we get this compression strain in our extreme compression fiber. We're going to assume we have yielding of steel. This is our force in the steel, and this is our force in the concrete. This is the value C, and this is the value A. The first thing we're going to do is we're going to isolate for this area of compressed concrete. So if you do this, we have 0.85 times AS, which is 1500, times Fy, which is 400. Then we have phi C, which is 0.65. This alpha 1 and beta 1, if you use F prime C equals 40 MPa in the equations, this is going to be 0.79, and this is going to be 0.87. So you have 0.65 times 0.79 times F prime C, which is 40, times this area of concrete in compression. You will get this equal to 24,829.6 millimeters squared. Now with this, we should solve for A and for this A bar. Okay, so if you look at this situation, this base is 600 millimeter and the height is 600 millimeter. So you have a triangle like this. Okay, so we just found this A is equal to 24,829. Okay, and this is the A value, and because the base is 600 and the height is 600, I know also this is A. So this 24,829 it's equal to a times a over 2, so it's equal to a squared over 2. So you can solve for a, and you're going to determine it's equal to 222.8 millimeters. Okay, next we should determine this moment arm. So normally this moment arm is equal to d minus a over 2 if we have a rectangular section, but we don't have this over here. So we need to use geometry to figure this out. So again, if you have this triangular section, where is the centroid gonna lie? So you can, if you have some complex shape, you have to determine the centroid like we saw in tutorial 2. But here, because I have this sort of triangle, I know this is at 2/3 a. Okay, so this value here is 2/3 a. So this z is just gonna be d minus this 2/3 a. Okay, so in our case, a bar is 2/3 a, and z is just d minus 2/3 a. We're going to use this a little bit later. So our MR in this case is just equal to this equation. Before I do this, I should check that yielding is occurring. So if we do C is just 222.8 divided by 0.9, and then let's divide that by D, which in our case is equal to 537.5. You do the calculation, it's equal to 0.41, and this is smaller than CD max, which is 0.64. So we do have yielding, so we can use this equation over here. So we have 0.85 times AS, which is 1,500, times FY, which is 400, and then we have Z, which is just D, 537.5, minus 2/3 A. So 2/3 times 222.8, and all this times 10 to the minus 6. You will find it's equal to 198.4 kilonewton meter. Example 2, skin reinforcement. For the deep beam shown below, determine if the beam requires skin reinforcement, and then detail the beam accordingly. Consider the beam to be used in an exterior exposure situation. You're given the cover is 40 millimeters, the stirrups are 10 m. We're told to use 15 m or 10 m bars for the skin reinforcement. In addition, you're given the beam dimensions, its effective depth, and the rebar that we've designed for moment resistance. This is the clause that discusses skin reinforcement, so you can read that for further details. But in summary, what it says is if your height of your beam is bigger than 750 millimeters, then you need to provide a amount of skin reinforcement which is equal to ASK, which is rho SK times ACS. ACS is the area of concrete along an exposed face. There's a specific formula that you need to use. You can check the figure on the next page. It explains how you get that. And we're going to go through an example now. And this rho SK depends on what type of exposure you have. So if you have exterior exposure, 10% of that area of concrete, you have to have that in steel as skin reinforcement. Okay, so this figure explains that formula. So this area ACS, you can think about it as having a height HCS and a width BCS. Okay, what's this height? Basically, you have to use this formula, so let's just calculate it. It's explained in the figure over here, but let's just calculate it based on this formula. So you have 0.5 times the height, which is 1,000, minus 2 times 1,000 minus D, which is 900 in this problem. This is equal to 300 millimeter. The next part is this BCS. So this BCS is just 2 times this X value. So if you zoom into this figure, okay, so what is this X? Okay, this X is simply the distance from this exterior face of your beam until the centroid of this skin reinforcement. So it's basically the cover plus the stirrups plus half of one of these skin reinforcement bars. So let's say we're using 15 m bars. Let's determine what this would be. So in this case, your X would just be 40 millimeter, that's your cover, plus 10 M stirrups, plus half a 15 M bar. That would give me 57.5 millimeters. I have two of these to get BCX, so that's just 2 times 57.5, that's 115 millimeter. Now I can find the area of this concrete that the code is telling me to consider, and what I'm going to do is I'm going to take a percentage of that area and I'm going to specify a certain amount of steel. But first let's find what this area is. So that's just HCS, which is 300, times this BCS, which is 115. If you do the calculation, you're going to find it's equal to 34,500 millimeters squared. Okay, we have two of these, right? So you have another one over here. So we need, for two sides, we're gonna need 69,000 millimeters squared. Okay, that's the area of concrete, but I want the area of steel. That depends on the exposure. So what I'm gonna do is I'm going to find this ASK, which is just equal to this rho SK, which depends on the exposure, times this area of concrete. So for exterior exposure, this is just 10%, so 0.01, not 10%, 1%. So 1%, so that's 0.01 times 69,000. I get 690 millimeters squared. Or I can say I need at least 345 millimeters squared of steel per side. Okay, so I have to see. So if I'm using 15 M bars, each 15 M bar is 200 millimeters squared. So that would tell me I need 215 M at maybe a spacing of 150 millimeters on center. How do I know the spacing? Okay, so if I look at this figure over here, this is, I said, is HSC. It's 300. Okay, so that's how I know how to space them. So I go, this would be 150 millimeter. You have 75 left over here. Okay, so that's per side. So that's what they're doing here. 15M, 15M over here. Or let's say if we're using 10M, then we would need 4 10M, because each 10M is 100 millimeters squared. So that would satisfy this. And I would space this at, for example, 75 millimeters on center. Okay, but for this example, we're going to use 215Ms. Where do you place this? This thing here, if you look at the previous figure, is just 2H minus D. So that's just 2 times 100 equal to 200. So that's how you know where you start this area over here. And then you would place those rebar in that area. So that's the example on skin reinforcement.